Welcome to Basic Electrical Engineering lecture series. This is a series of lecture videos for the first year engineering and electrical diploma students. In these videos, fundamentals of DC and AC circuits, network theorems, fundamentals of transformers, DC and AC machines, and renewable energy sources are the topics covered. Sufficient number of numericals are worked out in each session to make the concepts clear to the viewers. For a basic idea about the topics mentioned, please watch these videos from the very beginning itself. If you find the videos useful, please subscribe for the channel, like the video and press the bell icon for notification. Please try to wear a headphone and watch the video for better sound clarity. Thank you all. And now let's start with today's session. So in today's session, we are covering the fundamentals of transformers. So by definition, transformer is an AC static device that transfers electrical energy from one circuit to one or more circuits by changing voltage current levels without a change in frequency. That means it is an AC static device. This device transfers electrical energy from one circuit to one or more circuits. So the figure given here, it has got two windings. So it is transferring electrical energy from one circuit to another circuit, a second circuit. But there can be one more winding in the core. So in that case, so this we can call it primary, this one the secondary, and if a third winding is called there, we can call it tertiary. So in that case, if tertiary winding is present, then electrical energy is transferred from primary to secondary as well as tertiary. So that is the meaning of that statement. So it's a static device. Static device means not a rotating device. Static device that transfers electrical energy from one circuit to one or more circuits. There is no restriction that there should be only two circuits. So from the primary, energy can be transferred to secondary as well as to tertiary. And secondary and tertiary normally will be at different voltage levels. So one or more circuits by changing voltage current levels without a change in frequency. So transformer is used to supply electrical energy at a different voltage level. Say if 1000 kV AC is available and we want for our domestic purposes 230 volts, not 1000 kV, 1000 volts. So 1000 volts, we cannot use it for domestic purposes because most of our appliances are rated at 230 volts, 230 or 220 volts. So it is to be reduced to 220 volts. Then only we can operate our domestic appliances. So this 1000 volts is to be reduced to 220 volts. That is the purpose of transformer. So electrical energy is transferred from one circuit to one or more circuit by changing voltage levels. Once voltage level is changed, the current level also will change side by side. And this happens without a change in frequencies. In the primary circuit and in the secondary circuit, the frequency will be the same. Now, a transformer is shown in figure. This is a transformer. The essential parts are a core and two windings. One winding, let's call it as primary winding, the other one the secondary winding. Now, the purpose of core is to provide a tight magnetic coupling between these two coils. Unless the coils are tightly coupled, energy transfer will not be efficient. So the coil should be tightly coupled. There should be proper magnetic coupling between the primary and secondary circuits, electric circuits, or primary and secondary windings. For that purpose, this core is provided. So here a primary winding, a secondary winding terminals are kept open, and this is the core. Now primary is given an AC supply. Here this is an AC source. I'll write say the RMS value of voltage. V1 is the RMS value of input voltage. So when the source is connected to the winding, the current will pass through the circuit. I'll mark it as I1. These are RMS values only. See the direction of current I1. So I have marked the direction of current in the winding. So when current flows in this direction, it will set up a flux in the core. So this kind of current direction through the coil can set up a flux in this direction. That is a clockwise direction. A flux is set up in the clockwise direction. So for this current direction, the clockwise is the direction of flux set up in the core. So there is a flux set up in the core. So V1, it varies sinusoidally. I1 also varies sinusoidally, and the flux produced by the current, that also varies sinusoidally. So it is Vm sin omega t, or I is equal to Im sin omega t plus or minus phi, something like that. So phi also varies in a similar fashion. So from 0, it is going to a positive maximum, reduced to the magnitude of the flux reduces to 0. Then it goes to negative maximum, comes back to 0. The flux varies sinusoidally. So the polarity shown here is just instantaneous. Instantaneous means the alternating current, every half cycle the direction is changed at some particular point of time, at one instant. When this is positive, what will be the direction of current, what will be the direction of flux? That is what is shown in PCA. So polarity is only instantaneous. In the next half cycle, all polarity, the voltage polarity will reverse, current direction will change, the direction of flux also will reverse. So whatever polarity shown here is just instantaneous. So now what happens is that there is a flux set up in the core, and this flux is time varying. This is phi or phi m sin omega t. Let us take it like that. Phi m sin omega t. This is phi m. So this is a time varying flux, and this induces EMF in the primary winding as well as in the secondary winding. So in the primary winding, it induces an EMF E1, and in the secondary winding, it induces an EMF E2. Let us assume that primary has got N1 number of turns and the secondary has got N2 number of turns. The magnitude of E2 depends on N2. If N2 is more than N1, then E2 will be more than E1. It will be a step-up transformer. If N2 is less than N1, then E2 will be less. It will be a step-down transformer. So the circulating flux induces EMF in the primary winding as well as in the secondary winding. So in the primary winding, it induces an EMF E1. In the secondary winding, it induces an EMF E2. Now, the complete flux produced by the primary current will not complete its path through the core, or the entire flux produced by the primary current will not complete its path through the core, but a portion completes its path through air. So for example, take the primary winding, and this portion of the primary winding I have redrawn here, this limb, and see the current direction. So this limb I will draw once more. So here current is entering. This is the direction of current. Current is entering. Here current is leaving, and current is going into the plane of the paper. Current is coming out. Current is going into the plane of the paper, like that. So I have marked the current direction here. For this current direction, what is the direction of flux? If this is the direction of current through the conductor, so it will produce a flux like this. That is what I have marked here. So in these conductors will produce a flux in this direction shown. So this is the direction of flux produced by these conductors. And this is the net. But if you take the conductors on the other side, this is the direction. So this flux is called a leakage flux. So it completes its path partially through air and partially through the core. So the entire flux will not complete its path through the core, but a portion will complete the path through air. This is called leakage flux. So mutual flux, that is the main flux, that is phi, that induces an EMF in the winding, which is E1. Likewise, this leakage flux also induces an EMF in the winding. So in the primary circuit, this can be expressed as a voltage drop, that is I1 X1. The magnitude of I1 X1 is equal to the EMF induced by the leakage flux, EMF by leakage flux, or EMF induced by the leakage flux in the primary winding can be expressed as a voltage drop, I1 X1. So this reactance X1 is called the leakage reactance. X1 is called the leakage reactance. So the applied voltage in the primary side, it's V1. The coil will have, the primary winding will have resistance R1. So there will be a voltage drop in the resistance, which is I1 R1. Voltage drop in primary resistance, primary winding resistance. So applied voltage is V1, and in the circuit there will be a voltage drop I1 R1, this ohmic drop, or voltage drop in the primary winding resistance. Then there is a leakage reactance drop. Leakage reactance drop means it is nothing but the voltage induced by the EMF induced by the leakage flux. Both are equal in magnitude but opposite in direction. The EMF induced by the leakage flux, we are considering it as a voltage drop I1 X1, where X1 is called the leakage reactance. So I1 X1 is called the leakage reactance drop. Then voltage EMF induced by the main flux phi. So these three quantities are opposing V1, or the sum of these three quantities, the phasor sum of I1 R1 I1 X1 and E1 is equal to V1. So V1 is equal to I1 R1, I1 into R1 plus JX1 plus E1, or sum of all these phases is equal to V1. So primary applied voltage is V1. It is counterbalanced by the ohmic drop, leakage reactance drop, and the EMF induced by the mutual flux, or the flux through the main flux through the core. So here the secondary terminals are kept open. So E2 depends on N2. What is the whatever, depending on the number of turns in the secondary winding, and EMF is induced in it. There is no current in the secondary winding now because the terminals are open. Now, when the transformer is loaded, what happens? Let's check. Now, a load is connected to the secondary side. So, the applied voltage is V1. It induces so there is a circulating flux phi through the core. It induces an EMF E1 in the primary winding and E2 in the secondary winding. So when a load is connected, it takes a current, say I2. This current is I1. So I2 is the current taken by the load. Now what happens? Now when I2 flows through the secondary winding, there will be an MMF produced N2 into I2, that is the ampere turns on the secondary side. So this coil has got, or secondary winding has got N2 turns. So this will produce a flux. So the direction of I2 is such that when the secondary terminals are connected to load, a current will flow in the secondary winding, and the direction of the current is such that it opposes the main flux. So this is the direction of current. This is the direction of flux set up by the secondary current. Or the secondary will set up, secondary current will produce a flux which is opposing the main flux. Now, primary will draw a proportional current and set up an equal and opposite flux. So this I will take it as phi 2. Primary also will set up an equal and opposite amount of flux phi 2, so that this cancels out. That means through the core, the net flux at any point of time is equal to phi. When secondary current increases, then secondary flux also increases. So primary draws proportional current and set up an equal and opposite flux to cancel out the flux produced by the secondary, so that the net flux remains the same, that is phi. Always it remains phi in the core. Now, as in the primary, there is a current flowing through the secondary. There is a flux produced by it. As ampere turns, let's take it as N2I2. It produces a flux phi 2. And primary produces an equal and opposite amount of flux, so that it cancels out. But the entire flux phi 2 is not completing its path through the core. A certain amount leaks out, and there will be leakage flux on the secondary side also. There is leakage flux on the primary side. Just like that, there will be leakage flux like this on the secondary side also. So the secondary EMF induced in the winding, that's equal to E2. Then when current flows through it, when it is loaded, the secondary winding also has got resistance. There is a voltage drop in the secondary winding resistance, that is I2R2. Then the EMF induced by the leakage flux can be expressed as a voltage drop in the secondary circuit, that is I2X2. Then the remainder is V2. That means E2 is the induced EMF. If you subtract these voltage drops, we will get the terminal voltage V2. That is the voltage available here. This is V2. So I2R2 is the secondary ohmic drop or resistive drop. I2X2 secondary leakage reactance drop. V2 is the terminal voltage. So E2 minus these two quantities is equal to V2, phasor subtraction. So this X2 is called the secondary leakage reactance. So in primary as well as in the secondary side, primary Z1 is equal to, this is called the leakage impedance, R1 plus JX1. The secondary circuit total impedance Z2 is equal to R2 plus JX2. Or magnitude, only the magnitude if we want, then R1 square plus X1 square. Here the magnitude is R2 square plus X2 square. So Z1 and Z2 are called leakage impedances. Z1 leakage impedance of the primary circuit, Z2 leakage impedance of the secondary circuit. So the basic working principle of a transformer is that we are applying a voltage to the primary winding. So a current passes through the primary winding. It sets up a flux. This flux induces EMFs E1 and E2 in the primary and secondary windings. So when current passes through the primary, there will be different voltage drops. So when I1 passes through the winding resistance, the voltage drop produced is I1R1, resistive drop. Then the EMF induced by the leakage flux is expressed as a reactive drop in the primary circuit. This is I1X1. This is called the leakage reactance drop in the primary circuit. V1 minus these two quantities is equal to E1. Then the circulating flux induces an EMF E2 in the secondary winding. Just like primary, secondary winding works when current passes through the secondary winding. So secondary sets up a flux, but primary draws a current, a proportional current, and set up a counter flux, equal and opposite flux, so that it cancels out. And the flux through the core remains at the initial value always, at the no load value always. So the current set up by the secondary, the flux set up by the secondary also, it will not complete its path through the core. The complete flux, the entire flux will not complete the path through the core. A portion completes the path through air also, which is the secondary leakage flux. So the secondary leakage flux induces an EMF in the secondary circuit, and we can express it as a voltage drop, which is called the leakage reactance drop. This is the EMF induced by the leakage flux. Magnitude of I2X2 is the EMF induced by leakage flux. So E2 minus these two voltage drops will give you the terminal voltage V2. Now, the power losses in a transformer. Now, first one is copper loss. Copper loss means we have seen primary winding has a resistance, secondary winding has a resistance. Current through the primary winding is I1, current through the secondary winding is, we are taking it as I2. So what is I1 square R1? Power lost as power dissipated as heat in the primary winding. What is I2 square R2? Power dissipated as heat in the secondary winding. So these are the power dissipated in the primary and secondary as heat. This is called copper loss. So the power losses in a transformer, first one is copper loss. And copper loss depends on the magnitude of current. So in the primary circuit, current is I1. Primary circuit primary winding resistance is R1. So the power lost, power dissipated as heat in the primary circuit is I1 square R1. I2 is the secondary current and R2 is the resistance of the secondary winding. So power dissipated in the secondary circuit is I2 square R2. So add these two, that is the total copper loss in the transformer. So the next part is, first one is core loss, copper loss, second one is core loss. So transformer basically has got a core and two windings. So this is the power loss happening in the windings. When current flows through it, the winding will be having a resistance. Copper wire has a resistance and accordingly there will be certain amount of heat dissipated. That is called a copper loss. Then the next one is core loss. What is the power loss happening in the core? There are two components for core loss. One is hysteresis loss and B is eddy current loss. So what is hysteresis loss? So here one definition is given: when an external magnetic field is applied to a ferromagnetic material such as iron, the molecular magnet align themselves in the direction of the magnetic field. When the magnetizing force is removed, still a certain amount of magnetism remains in the core, the degree of which varies. So when an external magnetic field is applied to a ferromagnetic material, so we use a ferromagnetic material for the construction of transformer core. So transformer core, what happens is that when it is subjected to a magnetic field, the molecular magnet in the material will align themselves with the magnetic field. When we remove it, it will assume a random position. When the direction of magnetic field is reversed, then the alignment of the molecular magnet also will reverse. This is happening in every half cycle because the flux, this is the flux waveform. From zero it induces, it goes to a maximum, it reduces to zero, it goes to negative maximum, comes back to zero. So the magnetic field, magnetic flux density also varies in a similar way. Flux divided by cross-sectional area, this is a meter square. This is the cross-sectional area. That will give the flux density in the core. Now when the flux is in one direction, the molecular magnet will be aligned in one direction. When the flux reverses its direction, the molecular magnets also will reverse the direction. So this results in molecular friction which produces heat. This is known as hysteresis loss. The heat dissipated due to molecular friction is called hysteresis loss, and an approximate equation for hysteresis loss is eta Bmax raised to 1.6 into F watts per meter cube. Meter cube is the volume of the core, net volume of the core. So this is to be multiplied with the net volume of the core to get the total hysteresis loss. So the equation is so much watts per meter cubed. So F is the frequency of magnetic reversals. Here it is the supply frequency itself, because according to supply frequency only the flux also varies. Vmax is the maximum flux density to the power of 1.6. This is called hysteresis coefficient. So this is an approximate equation for hysteresis loss. And here a few materials are given which are used for the construction of a permanent magnet and as well as for transformer core. For permanent magnetic materials are, for example, alnico. Alnico is aluminium, nickel, copper. Then another material is samarium cobalt. Another one is neodymium and boron. These materials are used for the construction of permanent magnets. So its hysteresis loop is almost like this. So hysteresis loop is what is happening to the magnetic flux density in the core when magnetizing force is varied. Magnetizing force H is equal to Ni by L. So when magnetizing force is increased from zero, if the material is initially not magnetized, then the magnetization varies like this. And it reaches a maximum called saturation. So when magnetizing force is increased from zero, if the material is initially not magnetized, the flux density increases like this and reaches a constant which is called a saturation. Further, if we increase H also, B will not increase considerably or B will not vary at all, which the stage is called a saturation. When H is reduced, the flux density takes another path. So when H is reduced to zero, this is the flux density in the core. That means it is not, flux density is not coming back to zero even after the removal of complete magnetizing force. That is, we are increasing from zero to this value. At that time, this is the corresponding flux density. We are reducing H and bringing it back to zero. So the flux density follows another path. And here at this point, H is equal to zero. But still there are certain amount of flux density in the core. So this is called, this point is called point of retentivity. That means once the core is magnetized, even after removing the magnetizing force, the certain amount of flux magnetization remains in the core. Now if we increase H in the opposite direction, then the flux density reduces. At some point it will become zero. So that means when H is here, the flux density becomes zero. This is called point of coercivity. That means the amount of magnetizing force required in the opposite direction to wipe out the residual magnetic flux density. Now if we increase H further, we will reach again saturation in the negative direction. Then H is start decreasing further. It will go to here, it will reach the point of retentivity again in the opposite direction. Again H is increased in the positive direction, it comes back to this point. This is called a hysteresis loop. So these materials, that is the materials used for permanent magnet, which it will have a broader hysteresis loop. It is difficult to, large amount of negative force is required to wipe out the residual flux density. That means if such a material is used for transformer core, there will be considerable amount of heat generated due to hysteresis. So for transformer core, we prefer soft magnetic materials. So like silicon, steel, CRGO steel. CRGO means cold rolled green oriented steel. These are the materials generally used for the construction of transformer core. Its advantages are high permeability and resistivity. Then lower retentivity and lower coercivity. That is, the loop will be thin. So when the magnetizing force is reduced to zero also, from saturation value, it comes down to a lower level. So lower retentivity. So the loop is thinner, so lower coercivity. So if thinner hysteresis, because the area of the hysteresis loop is proportional to the hysteresis loss. So we prefer a material having a thinner hysteresis loop for the construction of transformer core. So why hysteresis loss is happening? It is because of the molecular friction. Because the molecular magnets are getting aligned in one direction during one half cycle and in the opposite direction during the other half cycle. And because of this continuous alignment change in one direction and in the opposite direction, there is molecular friction, and because of that, heat is getting generated in the core. This is known as hysteresis loss, and an approximate equation for that, eta Bmax raised to 1.6 into F watts per meter cube. Per meter cube net volume of the core. F is the frequency of magnetic reversals, that is, here it is supply frequency itself. Bmax is maximum flux density, that is flux through the core divided by cross-sectional area, net cross-sectional area, that is Bmax. Eta is called hysteresis coefficient. Then the next one is eddy current loss. Eddy current, meaning of eddy current is circulating current. Say in the core, this is the core, assume it is a solid core. This is the direction of B or flux. Now this is a time varying flux it induces an EMF in the core and circulates current. And these circulating currents are called eddy currents. This is the direction of the magnetic field. These are the circulating currents, which are known as eddy currents. Now, since it is a solid core, the magnitude of current will be high. Even a small induced EMF can circulate a large amount of current because it is a solid core. So, the higher the magnitude of eddy currents, the higher the eddy current loss, higher the amount of heat generated, or higher the eddy current losses are. So, to minimize eddy current losses, we are laminating the core. Laminating the core means, which will cover in the next session. That is, core is made up of lamination, thinner sheets. Now what happens is that instead of a solid core, if you are using thinner, thin laminations, then this will be the eddy currents. These are the eddy currents. Now here the magnitude of the eddy current will be comparatively less because it is thin, resistivity will be more. Resistance will be more, so the not resistivity, resistance will be more, and magnitude of eddy current will be less. Accordingly, eddy current loss also will be less. So eddy means circulating currents through the core. These currents are produced by the EMF induced by the time varying flux in the core itself. So even a small, if it is a solid core, even a small induced EMF can circulate a large current. So the core is made up of laminations. Between two lamination, there will be some sort of insulating material so that these two laminations are not in electrical contact. Electrically, they are to be separated. They should be separate. So here the resistance of the eddy current path is more. Therefore, the magnitude of the current will be less, and accordingly, eddy current loss will be less. So there are two major losses in the transformer. One is copper loss, which is the heat dissipation in the primary and secondary winding when current is flowing. I1 square R1 plus I2 square R2. Next is the heat loss happening in the core due to these two reasons. One is eddy current loss, one is hysteresis loss. Eddy current loss means the circulating current through the core due to the EMF induced by the flux. So to reduce that, we have to use proper laminations. We cannot use a solid core because of this reason. And instead of a solid core, if we use laminated core, then the magnitude of eddy current can be reduced considerably, and accordingly eddy current losses also. Then hysteresis loss by properly selecting a material for the core, a material which has got a thinner hysteresis loop. That will reduce the hysteresis loss. So these two are the major losses happening in the core, and eddy current loss can be reduced by laminating the core, and hysteresis loss can be reduced by selecting a suitable material for the core. Now that's all for today's session. Thank you very much for attending this session. If you like the session, then please share the video among your friends. Ask them to subscribe and press the notification, press the bell icon for notification. Thank you.